So, well, look, thanks for agreeing to do this. This is so
My
just
pleasure.
to give you some introduction. This is the end of the first week of the physics track of our summer school. This is only year 2 of our physics track because we only invented our theory of physics last year. The folks who are here are pretty physics educated in general, I would say. So we can assume various people are okay. Yeah, it's so we can assume decent. Okay, more somebody is saying more math than physics. Okay, all right. So what I thought we would try to do is I'd like to kind of go through. The ultimate goal is to understand how your kind of physics and string theory and so on, what do you now say you do? Do you now say you do string theory, or do you say you do something different? What is the category?
I never ever self-identified as a string theorist. String theory is a tool. You don't identify as a computer. Maybe you do. I don't know. Do you? Actually, maybe that is what you've been saying. But okay, let's I'm interested in basic problems in physics, quantum gravity, black holes, and string theory has certainly been the tool that we've gotten the most from.
Okay, but no string theory moniker for the whole thing. But so I'm curious. I mean, we've known each other now for basically 40 years, and I guess one thing might be interesting to people here is to understand a bit of the trajectory, your trajectory, and the trajectory of physics over that period of time. I mean, I think when we first met, you were maybe working with Roman Jakif at MIT, doing some kind of quantum field theory. What were you doing? What was your thesis about? I should know, but
my thesis was about large N QCD, and something which came back with a vengeance many decades later, a subject.
Right.
I was working on. I was really interested in quantum gravity, and but my advisor told me I would never get a job if I worked on that, and as did many other people at that time. You can remember the attitude about quantum gravity then, and
we should explain to people here what that attitude was. I mean, basically, perturbation theory was, it wasn't going to be renormalizable in its obvious form. One wasn't going to be able to set up a whole Feynman diagram story for it, or do the standard things that one expected in field theory. So then, what was one supposed to do? Is that a fair summary of how people felt about it, or what was your characterization of why people thought quantum gravity was doomed at that time?
I don't think it has a logical. I can tell you what they said, but I don't think it has a logical scientific explanation. And indeed, I think most of the things that are done and that young people are told to do in physics, including now, by people who work in string theory or related things, it's really not based on, there's just a little bit of logic in it. It's mostly sort of fashion and, quantum gravity at that time was clearly, I mean, it had been identified by Pauli in the 50s as like, we have this amazing machine, quantum field theory, that works for everything. It works for, well, now of course we know it works for the strong and electroweak forces, been tested now to 16 decimal places, and it doesn't work for quantum, but it doesn't work for general relativity. There's no, good reconciliation of quantum mechanics. And
right, but that time, people's attempt to do that involved thinking of the graviton like the photon, and then finding out that the theories you got from doing that, the most obvious theories you got from doing that, didn't have the properties that people thought they should have to let one do the mathematical developments that they could do for things like quantum electrodynamics and so on. And but what did people say? I'm curious, when you said, I want to work on quantum gravity back in late 1970s, they said, you're crazy because?
Well, they said well, I literally quoted you, Roman Jakiv, you'll never get a job.
Okay, so that's a meta statement.
That's a meta statement. But already at that time, string theory, we're talking in the early 80s. Already at that time, string theory had shown in 72 that you could, when I was in high school and you were in kindergarten or whatever, and they'd already shown that string theory could put together quantum mechanics and general relativity. And it was a problem in which there were many rich directions to go in, to explore. And it was not long after Hawking's work, which opened up all kinds of interesting questions. So it was an obviously very rich field, but the tradition, there was a very strong tradition in particle physics, which you are very well aware of, that went on for many decades of building accelerators, finding new particles, understanding the laws that govern them, and finding new laws, getting Nobel Prizes, whatever. That was particle physics. And if you weren't part of that enterprise, it wasn't, the number of people who were interested in quantum gravity then, even with the stuff that Hawking did, but it's dozens in the world.
Right.
And whereas particle physics at that time was thousands.
Right. But let's go back to the origins of string theory, because I mean the original, late 1950s, early 1960s, the whole sort of idea of how should one model strong interactions, and the whole Reggie calculus thing, and the sort of elaborations of that. I mean, as I remember it, the first time I heard about string theory was as part of a development from, we can't use sort of, things like in quantum electrodynamics, we could just sort of count the number of photon interactions that happen. And, but in strong interactions, we couldn't do that. And so like, how are we going to describe this? We just say there's an S matrix and it has certain properties. And then that, and somehow out of all of that came ideas about string theory. What was the story there?
Yeah, well, it's an incredibly interesting history. So in the late 60s, I guess Veneziano, many people would call that the beginning of string theory. He wrote down the Veneziano formula, which was, they were trying to understand, they were trying all kinds of methods to understand the scattering of hadrons. That was the big unsolved problem then. Scatter hadrons, mesons, stuff comes out. There was no theory that described it. This is the theory of the strong interactions. And it was noticed that the spectrum of particles, there was some formulas written down that were approximate formulas, and it was noticed that the spectrum of particles look literally like the resonances of a string. So string, if you have an elementary object, which is a string, it's just like a guitar string, right? You can make it C, you can make it go an octave, you get these resonant frequencies of a string. And so elementary strings also have resonant frequency. And so there was a proposal which kind of worked, but it didn't work that well quantitatively to explain the spectrum and scattering of elementary particles. And then
let me just to take that back a little bit. I mean, so So, one of the things that had happened was this idea of
Nothing to do with quantum gravity. This original
yes, and no,
nothing to do with quantum gravity.
Right.
Yeah.
I mean, so the original thing was, as I recall, this idea of Reggie trajectories,
Exactly.
which is an idea that I don't know what's happened. One of the things there was, you have particles like the pion, which is spin 0, the rho meson, which is spin 1, the F meson, which is spin 2, and these things have successively higher masses. And people made these plots of, spin versus mass, or mass versus spin, and they would follow straight lines or parabolic trajectories or whatever else. And people thought that was significant. And then there was this idea, which I don't know whether that's come back, of complex angular momenta. The theory of, is that a thing these days? Do people care about complex angular momenta these days?
Yeah, they do actually.
Okay, I want to learn about that again, because we care about something related to that now too.
Yeah.
But I just got a copy of Reggie's book about scattering theory, which is now deeply out of print, because I thought that might tell me something about where that came from.
Yeah.
But okay, so there were these trajectories where there was these different mesons that were supposed to be carriers of the strong force and things like that were arranged in these Reggie trajectories, and that's the thing that people were saying, this looks like excitations of a string. Is that right?
So then what happened was the theory of the strong interactions, QCD, Gelman, Gross, Politzer, Wilczek, whatever. It was understood that the strong interactions were described by Yang-Mills theory. Now, interestingly, Yang-Mills theory had been discovered 10, 20,
1956, I think. Yeah, 1956, I think, was the Yang-Mills paper.
Yang-Mills? No, 50s, wasn't it?
Yeah, 56.
Oh, 56. I thought you said 30s.
Yeah.
And they were trying to explain the relationship between the neutron and the proton. So it was invented for another reason that was wrong, but then it was used. So this often happens in physics, right? Things are discovered in one way because of this synergy between mathematics and physics that, consistent mathematical structures are very rare. And if they find one place in one part of, don't find their place in one part of physics, they can wind up back in another. Okay, so Yang-Mills theory ended up being a very good quantitative description of the strong interactions at high energies in accelerators, what happens when you smash protons to each other at high energies. And if you had asked somebody, and this was accepted as this theory of strong interactions, if you'd ask somebody in the late 70s or at the time I was doing my thesis, how they would summarize this, and they would say, well, the SU3 theory of the strong interactions, QCD, is the correct description, and string theory is the wrong description. Now people would say it somewhat differently, actually. So one of the things that we've understood is that there can be many correct descriptions, and they're good. They're parameters in descriptions, how strongly things interact, the strength of some interaction. And QCD was good because the parameter that controlled it, the coupling between the quarks and the gluons, is small at high energies. And so you get a good analytic approximation. But if you go to low energies and you want to describe bound states like protons and mesons and so on, QCD becomes very difficult. And, there's been a lot of work on it. It's not you can, with enough computer time and so on, use it to describe these other regimes of the theory. And some people still think that there's some sense in which there is a string theory of the strong interactions, that it's just the parameter isn't small in the regime of interest, and so it's not an exact, not such a quantitatively useful description. But
maybe, I mean, obviously in very recent times, whether it's in amplitude hedron business or whatever else, it's come back because, string theory ideas seem to actually be applicable potentially to answering questions about QCD and strong interactions and so on. But
Absolutely.
But I mean, going back to the history, it's something I'm curious about, and maybe the thought was back in the in the 60s and so on, that forget trying to sort of compute sort of step by step how interactions like strong interactions worked. Just think about the S matrix, the scattering matrix, the thing that describes the interaction, and then describe certain properties of the S matrix and say, given those properties, we can kind of home in on how the interactions have to work. And as I recall, the original Veneziano model was a particular ansatz for how the S matrix would be structured.
Right, right.
But so did that describe, was there a thought that excuse me. Was there a thought that described interacting strings in some way? I mean, because the original ansatz looked like it was just this single thing with a bunch of gamma functions and so on that seemed like a description of a static object. What was the sense in which that described interacting strings?
Okay, so he just wrote down, he did exactly what you just said. He assumed some analyticity properties, which turn out to not quite be valid in the real world, as in the real world describing interactions of protons. He assumed these analyticity properties and then solved them to get, but they might be approximately true, but then solved them. And he came up with a formula for Veneziano amplitude, which only, I think it was another 5 years before Nambu and Godot and Susskind realized that this was a theory of the scattering of strings. So the formula for this S matrix, for the scattering matrix, was there long before it was understood to be describing the scattering of strings.
But so in what sense, I mean, okay, what was the, what was the kind of physical intuition behind this kind of theory of the scattering of strings? Because that was long before like things like string field theory and so on, I think. I mean, that was just a, how did that work? I mean, so because I remember people talking about, extended objects in quantum mechanics. Strings are the first example of extended objects in quantum mechanics. We have point particle quantum mechanics. Now we have to extend that to dealing with the quantum mechanics of extended objects. Yeah. And that seemed to be an early focus of why one should care about.
That's not how Veneziano got started.
I know that. Yeah, I know that.
He got started,
by looking at properties of gamma functions. I mean, he was just doing
properties of scattering amplitudes. He wanted to be able to have a single scattering amplitude that had the property that you could think of it, the 4-point scattering, as you take, you scatter two objects, they make a third that propagates and then decays, and you sum over all such possibilities. And then that should equal the same thing where you sum over all exchanged particles. Now, that isn't true in Feynman diagrams. In Feynman diagrams, you sum up both kinds of processes.
This is the crossing symmetry idea of strong interactions. This is the idea of crossing symmetry, that you could have that S channel and T channel, that it will be equivalent to think about it as S channel, as producing a particle versus exchanging a particle.
Yeah. The word crossing symmetry is used in different ways. It wouldn't usually be, but that's the right idea. Yeah.
I thought that was it's used in modern bootstrapology, right? Is it used in a different sense?
Modern right. So it's a property of two-dimensional conformal field theories that this is always true, but it's not true in the standard model. But there's another kind of crossing symmetry where this is getting a little technical, but there's another kind of crossing symmetry where you compute some scattering amplitude, and then you consider the same amplitude where exchange an incoming and outgoing particle.
Oh yeah, right.
Those are equal by some. Those are equal in some way. That's
what is the S channel T channel equivalence? What was that called? Did that have a different name?
I guess that would be ST channel duality. I guess that would be what they would.
I think at one time it was called crossing symmetry.
It might well have been called cross. It may well have.
I've been asleep for 40 years. So,
right. Yeah, so, these words change their meaning. It's used a little differently now.
Okay, fair enough. But
yeah.
But the interpretation, the physical interpretation of these extended quantum mechanical things scattering had nothing to do with the original Veneziano version. But what was the, I mean, what can you describe sort of the intuition of how you can compute, why is it the case that, you know, if you have some actual sort of physical string-like thing, that its scattering amplitude follows that kind of formula?
Yeah, so okay, so if you have let's see how well this works. If you have, I had a blackboard in here, but it's not in here right now. Okay, so let's imagine we have two strings.
You have to, let's see, let me just pin this and label.
I'm gonna draw it and then hold it up. So let me draw two pictures of string scattering. So here we have AB goes to CD, okay?
Slightly further away. Yep. Okay. Yes.
Okay. So in this picture, it looks like string A and string B join. Let's call it F. They form string F, which then decays back to C and D. Okay. But I could have drawn this. Okay, this is a very simple picture, but you can really make this into very precise mathematics. I could have drawn this somewhat differently. Because I could have drawn it like this. Now here I have A and B exchanging E and then scattering into C and D. And there's no difference between these pictures, because what we do when we compute this process is we actually we fix the initial and final strings, and we sum over all world sheets that go in between. So you don't want to both sum over, that would be double counting if you were to both, is that?
We saw it, I saw it at least once, yes. Hopefully, yeah, there we go. There's the lower.
There's string exchange, right. And there's string creation and decay. And they're topologically the same.
Mm-hmm.
And when you actually compute this thing, what you do is you fix the initial strings and the final strings, and then sum over all the possible world sheet configurations that interpolate between them. So,
well, you were explaining that the point there is that explains this duality, not the same kind of duality as people talk about now as duality, but this duality between exchanging particles and turning into a particle.
So Veneziano just wrote down the formula. I don't know exactly. He was, there were all kinds of things going on in physics, and I don't know exactly. I'm sure he's written about it exactly what it's motivated him to write down this formula. but it is a magic formula that has all kinds of magical properties and keeps coming up over and over again. And then, of course, what happened, and that now we understand in very simple terms why his formula was a formula for string scattering, because a formula for string scattering would manifestly have this property. But then they tried to make this more and more string scattering more and more precise, and to get really good solid formulas. And they found that in order for everything to totally fit together in a tight way, they found some very strange constraints. This was now getting into the early 70s, after string theory had been dropped. String theory had been was being dropped as a theory that described the strong interactions, but people were mesmerized by the amazing mathematical structures of these formulas. And then they realized that, that no matter what you did, there was always a spin tube particle, and that was the graviton. So you cannot write a consistent theory of this type that does not have gravity in it.
But so when you talk about a particle, I mean, these are, we've got some world sheet, and that world sheet has certain kind of, you can decompose the motion of that world sheet in terms of modes of some kind, presumably. And what you're talking about is some property of those modes of the world sheet.
That's right. Each mode is a separate particle. Most of the modes are very high energy, which, if you work it out, means that if we think of the individual high energy mode as a particle, it's a very massive particle. And so likely something we wouldn't have observed. But then there's a very interesting spectrum of low-lying particles. And what really was irritating everybody at that time was that there was this massless spin 2 particle, and nobody had ever seen a massless spin 2 particle in the strong interactions. There was massive spin 2 particles, but no massless ones.
So tell us, how do you identify? You're looking at this world sheet, and you're looking at the modes of the world sheet. How do you identify spin from that?
Well, you mean, you just, how do you identify spin from that? Well, it's no different than identifying the energy, right? It's a conserved quantity. There's an energy density on the string. It can be rotating like this. And once you know the configuration, you just use, it's just special relativity, really.
Wait a minute. So you're identifying spin. What you've got there is a world sheet where you've got, in that case, you've got closed strings making these tubes. And are you thinking of the angular momentum of the thing? I mean, so the particles, as I understand it, are, in that world sheet, the particles are fluctuations of that world sheet. Is that true? Yeah.
So the lowest line, so there's one fluctuation of the world sheet. So I would call it the fluctuations of the string, not of, well,
okay, it's a string, but it's
so you can imagine a string that is beating in a spherical symmetric, in an axial symmetric fashion, just kind of expanding and contracting and expanding and contracting like this. That wouldn't have any angular momentum.
Mm-hmm.
But you could compute its energy just from, you just would take the individual, it has a tension, it's Newtonian mechanics, really. Well, okay, it's all done in a relativistic way, but it's got a tension per unit length, and so it has rest energy, and then it also has kinetic energy. So that's how you learn what its energy is.
Mm-hmm.
The angular momentum, it can actually literally start spinning around on itself like that, and then it has angular momentum.
But it's okay. And why is its angular momentum quantized, for example? Well, this is not yet a theory of quantized strings. This is a theory of why are there, why is, I can see why, I mean, you know, when you have a string which is of fixed size or something, it has quantized modes for the same reason that a violin string has quantized modes, so to speak. In that description you just gave, why is the angular momentum quantized?
Well, so, you know, you should think of the string as, for a classical string, angular momentum is not quantized. The same reason it isn't for a classical point particle. So then we have a wave function for the string, and the eigenvalues of angular momentum acting on that wave function have to be quantized for the usual reasons.
Well, I mean, that's kind of an ansatz in quantum mechanics of point particles. That there is, I mean, that's the setup of quantum mechanics. But
this is quantum mechanics.
But why? I mean, when you have an extended object like that, why is it obvious why the standard? I mean, what is the you know, normally angular momentum
you demand that the wave function be single valued under 2 pi rotations.
Okay, so it's the same reason. It's the conjugate variable to angle.
If you have a point particle moving in a bowl, its angular classical point particle isn't, its angular momentum isn't quantized. But if you write the wave function of the point particle, the quantum states of the particle moving in the bowl, both the energy levels and the angular momentum will be quantized.
Okay, so the big point here was that there was, so there's, is there a
not even the energy will be quantized if you don't
have some constraint on the,
and then you would have a continuum of states of the string rather than a discrete tower of states.
But so what leads to the quantization of states in the string is having a fixed size of string in some way?
No. What the string can change its size, it has a tension. So it can change its size, it has an energy per unit length.
Yes.
But of course it has to conserve energy. So it has some tension. If it can't just sort of, you know, if it gets bigger, it has to lose some kinetic energy. So it will oscillate. And quantum mechanics will quantize the allowed spectrum of oscillations just as it quantize the allowed spectrum of oscillations of a particle moving in a harmonic oscillator.
Fair enough. So okay, so when it was, you know, back in 1972, you're describing, you know, people look at strings and the action for strings and so on, and observe that there are sort of elementary excitations that correspond to massless spin 2 particles. What about other spins? Were there also massless particles of other spins?
Well, yeah. So ultimately, there are also non-abelian. So at the end of the day, I mean, it's a long story how all of this was understood, but at the end of the day, there's everything that we observe in nature. Everything that we observe in nature can be there.
I thought, why can't everything be there? Why can't all possible spins be there?
Massless?
Let's say. I don't know what determines, you know, one would think from the setup, one would think that one would just find massless excitations of any spin. Why doesn't that happen? Or does it happen?
Well, there is something called the tensionless string, in which you set the tension to 0. It's a kind of a singular object. People are interested in it. There's a lot of symmetry in that theory that's not very well understood. Actually, there's been some progress on it just in the last year, but that's not usually what people are thinking of when they talk about string theory. It's just that if you, yeah, okay, here's the answer to your question. So as it gets more energetic, as you go to higher and higher vibrational modes, the energy of the thing rises, and the mass squared, that translates into a rising mass squared. So in general, you would expect that more rapidly spinning things are higher and higher mass. And indeed, that is the whole Reggie trajectory thing, right? You go up, and as you go to higher and higher spins, the Reggie bound is some linearly mass that grows linearly with the spin. So that leaves the question, but then you might ask the other question, well, hold on, the graviton is spinning. Why doesn't it have a mass? And the reason it doesn't have a mass is that there's an offset right at the beginning coming from the Casimir energy of the string. And there's something very special that happens for just a finite number of these oscillatory modes, that the energy from the spin exactly cancels, the positive energy from the spin exactly cancels this negative Casimir energy, and that gives us some finite number of massless particles.
So okay, so you could change. I mean, this is like normal ordering in standard field theory, where you're setting the 0 of energy in some way. Is that true?
Yeah.
Right. And so
yeah, but I'm probably not going to agree with what you're about to say.
Okay. Could you set the 0 of energy to give you a massless spin 3 particle instead of a massless spin 2 particle?
Okay, they tried to do that back then, and they tried to do that to get it to agree with the strong interactions. The problem is that if you do that, you get an anomaly in Lorentz invariance. And you get some kind of theory which is, as far as we know, inconsistent. So there are many kinds of consistency constraints on this story. Anomalies are a big deal. You have to cancel them, and that leaves us with just a few possibilities. And so, so it's an exciting thing that the few possibilities not only include but insist on theories with a graviton and therefore general relativity.
So one thing I'm confused by, when you talk about Casimir energies, that's a quantum field theory effect. I mean, the Casimir energy is a sum over all possible modes of the field. And so are you saying that when you set the 0 of energy for the strings, that what you're looking at is you're saying, look at some energy sum from all possible modes. And that's, I mean, how does that relate? Can you actually compute this Casimir energy, or is it more like a kind of a renormalization type idea where you just say, we've got this bare original energy for the string and we're going to subtract this constant?
You can compute it. So what you have, you have a string, and there's a field at every, a field which represents the position of, you can think of a string, in an interval going from 0 to 2 pi, and then you have a field x of sigma that lives on the string, and that field describes the position of the string in space-time. So the location of the string is the location of every point along the string is a quantum field in the 1+1 dimensional theory of the string world sheet. And then you compute Casimir energies in the standard way in that 1+1 dimensional field theory.
Where you're comparing, I mean, because usually in the Casimir effect, you're comparing, the modes inside the box with the modes outside the box. So in this case, you're comparing the modes for a finite size string with the modes for an infinite size string or something. Is that how it works?
Yeah, yeah.
But okay, so then, but this consistency condition, when you talk about anomalies, I mean, what I remember from maybe a different consistency issue for strings had to do with tachyonically propagating excitations. But the thing you're talking about is actual anomalies like quantum field theory anomalies, or not. When you said anomalies that happen if you try to set the zero of energy to not correspond to the spin 2 excitation being zero energy.
Well, I'm using the word anomaly to refer to any classical property that isn't preserved when the theory is quantized.
Okay, but so then you say some pathology happens when you try and set the zero of energy to not end up with the spin 2 excitations being of zero mass, then you get some
You get a pathology. Yeah.
Okay. Is that pathology? I mean, I remember there's a pathology, maybe that's from the dimension of the of space-time, that you get a pathology about tachyonically propagating modes.
Oh, yeah. So, right. Okay. There are many different, there are many different consistency constraints. And it's surprising that you can, I mean, I think it presumably looked to people in the late 60s, early 70s, they expected that there would be no way, that somehow strings were some approximate phenomenological concept, and that there would be no way to have an exact quantum theory of strings. So all of the things that you're saying are correct. They're just different statements. So now there's the problem of the tachyon, and so if you want to have Lorentz invariance and not have a tachyon, you need to also dress up the string by putting extra fermionic degrees of freedom that live on there. So we had one field that lived on there, which is a position, and then we need another field, which is a fermion, to make everything consistent. And in fact, it had to be supersymmetric. And in fact, this is how supersymmetry was discovered.
That was with the supergravity business. That was the thing from the 1970s. Is that right?
What I'm talking about now is 71, 72. I don't know the exact. This was 5 years before supergravity.
Okay.
This was even before global. This was the first, really the first. The Nuvo-Schwarz string was, I believe, prior to the West-Zumino. Yeah, the West-Zumino site. So it's an interesting example of sort of the unity of physics. Supersymmetry, of course, has been interesting for many other reasons. And it's an interesting example of how you start someplace, you end up, I mean, you were talking about that in your writings. You started on the physics project for physics, do something on physics, and then you learned that it, had other kinds of, so all about this. Everybody knows about this, right? But we keep forgetting it. You have to take it. You have to take the science where it leads you. And so here they were trying to solve the strong interactions. It didn't work, but they might have solved an even bigger problem that actually nobody was interested in, quantum gravity. And
okay,
yeah.
but so historically then, this idea of supersymmetry, symmetry between bosonic degrees of freedom, fermionic degrees of freedom, was I don't remember all this history. That was early 70s. Then the idea of using that to have a theory with particles, with fermionic particles, along with a graviton-like thing. That was the sort of supergravity idea. And then, but then somehow, somewhere in the middle of that, supergravity only worked in 26 dimensions and so on. When was that? Was that known from the beginning?
You know, that's kind of an interesting question, because I don't quite know how that, it wasn't very long. I think supergravity was around, you know, it was 3 years later. So it was, once you had the supersymmetry, you had string theory, it had a graviton, it was supersymmetric. It was pretty clear that there had to be something called supergravity, and when people went out and looked for it, and they found it. Yeah, and you needed actually, you know, the theory in 26 dimensions is not a fully consistent theory. It has a tachyon in it. It's unstable. So if you want to get rid of that, you need supersymmetry, and then you're in 10 dimensions.
Okay. So, okay, maybe we should skip, because I'm really interested to get to more modern stuff, because I mean, this is kind of the earliest epoch, or the first two epochs of string theory. I mean, first the strong interaction thing, then the supergravity thing, but now things, I mean, you know, this is now going to after when I stopped paying so much attention to this stuff, and when, you know, for years I would ask you, when should I learn about string theory, and you would tell me, not yet. So it's okay, well, but so then what happened? I mean, can you just run through roughly the history that led
okay
to...
so then interestingly, there was very strong evidence, not really a proof, but there was very strong evidence in the early 70s that there was a consistent quantum theory of gravity that came out of string theory. But there was something which ultimately was announced as a proof that string theory could never have a theory that violates parity, could never produce a theory that violates parity in the way, you know, Li-Yang parity violation. So its status from, you know, it's from the understanding that it could describe quantum mechanics and gravity from 1972 was, you know, as a toy model.
But so is what went wrong? I mean, like, you know, one way to understand the parity violation is that neutrinos, if they're massless, can be chiral. You know, there's only a left-handed neutrino, so to speak. Is that so? In these excitations and these fermionic excitations on strings, was it the case that you could essentially never get a chiral, you know, a single chirality excitation on the string? Was that the nature of was that the type of problem?
Yeah, that string theory could never produce that. And then
because there'd always be both chiralities. It could never select one chirality. Was that sort of the issue?
Yeah, but why that should be true is very, very complicated. Why that should be true, and I guess there was a proof of it announced by Alvarez, Gomez, and Witten in '83, something like that. And that proof. And so at that time, during that decade, I'm going to say there were 10 people in the world working on string theory.
Were you one of those people, or were you not yet in that business?
I got into the business, you know, I got into the business 2 years before I got into the business right around the time we met.
Okay.
And I was interested in quantum gravity, but the string theory stuff, I remember Mike Green so I thought, okay, I'm interested in quantum gravity. They think they have something to say about it. I better understand what they're doing. So I got out, it was like, I felt like it was my duty to educate myself about it. And I remember Mike Green, who I don't know if the rest of you know, you're Green and Schwartz or the.
Yeah, I remember Mike Green. Yes,
Yeah,
always
of course
used
you
to wear
remember.
leather jackets.
I don't know that all the other people on the screen know he is, but he's one of the founders of string theory, and he and John Schwartz were really kind of the heroes during that period. And so
they weren't heroes at all. They were off in the wilderness.
They were off in the wilderness, but now they look like heroes, And so Mike Green was visiting the Institute giving lectures on string theory, and they put him in the desk next to mine in my office there in D building. And I was talking to him, and I remember saying to him, but isn't it just, I didn't like it. I felt I had to learn it, but it was all so complicated and all this stuff. And I remember saying to him, isn't it just really ugly? All these moves. I was at that time, and of course I was wrong. I thought that what we needed for quantum gravity was just some, and this may ultimately look true in the, when we look back on things, but I thought what we needed for quantum gravity was some fundamental new principle, like what happened with quantum mechanics, the uncertainty principle, or the equivalence principle. I thought it would be something that we would create. I didn't think it would be some long list of formulas and numbers of dimensions and extra little gadgets on a world.
Yeah, I don't think it is. I think in the end it isn't. And I think you probably think that now.
It may or may not be, but what I think I was wrong about then was whether we can learn something by studying it, and whether we can get that, whether it can jog our thinking around, and whether we can learn that, whether it's a fruitful enterprise to study it. And I've become convinced that it is, without sort of buying the idea that, okay, the real world is really made up out of strings,
Okay, so what happened? So, okay, the 1980s, people were sort of off in the wilderness. This parity violation problem was a blocker. And then, so what happened next?
Well, so what happened next was, and this happened when you and I were both at the Institute, there were three things that happened at the same time. There was a new form of string theory discovered. Most importantly was Green and Schwartz found a loophole in the proof that you couldn't have parity violation, a very subtle mathematical loophole that I can't describe in a slogan. It's just like some subtle topological term that was missed in the analysis. But it was a loophole that you could drive a tractor trailer through, and once you found it. And then the fact that string theories want to be on Calabi-Yau spaces, the connection to Calabi-Yau spaces, that was what I did with Candelas, Horowitz, and Witten. And then all of a sudden, we had all kinds of ways of getting string theories in 4 dimensions that had matter structures that looked very much like what we encounter in the real world.
So can you say something about
all of a sudden,
yeah,
string theory became, I sometimes present a little string theory report card when I give public lectures. And I have one line which says, testable predictions, F. Not being ruled out as a theory of the real world, A.
Right. So
they're different things, but yeah.
But back to the Calabi-Yau business, because that I think I sort of, I stopped paying attention to this field right around the time that happened. So this
Yeah.
so the Calabi-Yau manifolds, these are things which you get as solutions to like vacuum Einstein equations and things like that. Is that
Right? Right.
And so in what sense, what do you mean by strings living on those? You mean a string where instead of being in a background space-time that is flat space, it's in a background space-time that corresponds to one of these solutions to the vacuum Einstein equations. Is that what you mean?
That's right. So the consistency of string theory is incredibly delicate, and you can't just put it on any space-time. They choose which space-times they like, and it turned out that they choose this special kind of space-time, which had only been, at that point, Yau had proven their existence, gotten the Fields Medal for it only maybe 5 years earlier. So this was also a wonderful example of sort of confluence between mathematics and physics. And string theory liked these spaces. And when you looked at properties of string theory on these spaces, bingo, they had exactly this sort of parity violating kind of structure that
I love the way you describe the string theory as liking this. It's like the habitat of some animal, that it goes, it goes to those particular kinds of spacetimes. But what is the characterization? What is the relationship between Calabi-Yau manifolds and solutions to Einstein's equations?
They are solutions to the Einstein equation. Yeah, they're solutions to the Einstein's equations, but they're very special ones that, it had been, they have special mathematical properties, certain topological properties that had made them of interest to central topic in mathematics since, I guess, the 50s, since the Calabi conjecture was probably the 50s. Yeah.
But so it was not the case that any old vacuum solution to the Einstein equations, any space-time which was a vacuum solution to the Einstein equations, that strings didn't like living on all of those. They only liked living on particular ones that had particular properties.
Well, what's special about these is that what you want, what's special about these is that you still preserve supersymmetry.
Okay.
So you start out in 10 dimensions. Well, I mean, so strings can live on many spaces. So it's not that these are the only kinds of spaces that they can live in, but the first thing you want is, you don't want 10 dimensions, you want 4 dimensions. So you want to get rid of 6 dimensions. And so that's called compactifying. So you curl them up. So you curl up 6 of the 10 dimensions. And
as a kind of distant observer of scientific progress, that has to be a kludge. But be that as it may, by the time you say it would naturally be in 10 dimensions, but we curl 6 of them up, it doesn't sound promising. But anyway, I understand that that's a mathematical method that you can use to get to that. But how does that relate to the Calabi-Yau manifolds?
Well, I agree with that, Stephen. If you're asking the question, is string theory predicting? If you're asking the question, is string theory predicting from some first principles 4 dimensions with the standard model plus general relativity? The answer to that is a resounding no. That's not a prediction of string theory. Okay, but there's a different question. Is there any configuration of string theory?
Fair enough.
That is 4 dimensions? And it was believed that the answer to that question was no.
Mm-hmm.
And so the fact that the answer to that question wasn't no is interesting. Yeah, so I'm not trying to argue that 4 dimensions is a
But
prediction of
so,
string theory, but
just so I understand, I mean, the existence of these gravitons or, massless spin-2 excitations on the string, and the fact that the string can live in a background space-time that is a solution to Einstein's equations, what's the relationship between those two statements, if any?
wait, ask the question again. Which two statements?
So I mean, insofar you've got two different indications of a role of gravity. One is that there are massless excitations, massless spin-2 excitations of the string. And the other is that the string can happily live in a classical background space-time that solves the Einstein equations. Is there a relationship between those two different kind of indications of some relevance to gravity?
I mean, it's very hard to imagine. They're two sides of the same coin. It's hard to imagine that one could be true without the other.
Okay.
Because once you say there's a spin-2 particle, we can use Feynman's famous argument from the early 60s that general relativity is the only consistent interacting theory with a spin-2 particle. So once you say there's a spin-2 particle and there's a graviton, you get gravity, and so
you get higher order terms, right? I mean, the Lagrangian doesn't have to have just that. Can't you? The argument about consistency of a theory with a spin-2 particle, it could have all kinds of higher order weird things beyond the Einstein-Hilbert action, I think.
Higher dimension operators.
Yeah.
Yeah, and those are there. And the Calabi-Yau spaces solve the whole series.
Okay. So anyway, so we should keep going with this history because I really want to get to the more modern stuff. So then you figured out this thing about Calabi-Yau manifolds. Then what happened next?
Okay, so then what happened next was there was a kind of, I think there was a sort of so then it can only partially be described by science, partially by sociology. People looked at this as sort of the next step in sort of the reductionist program of finding all the laws of physics that we started out with the electromagnetic force and QED, and then we had the weak force and electric force, and now this was like the next thing. And people, then there was a lot of work really trying to make predictions for accelerators, and that continues to this day. I don't think it's a very fruitful exercise.
You're betting against super partners, all these gluinos and all that kind of thing. You don't think that there'll be an announcement next week that somebody has observed a super partner of one of the known particles?
Well, that's a slightly different issue because you could have supersymmetry without string theory. Mm-hmm. And so if you found such a thing, it certainly string theorists would declare victory, but but I don't know if it really would be a victory. And moreover, there's so many different Calabi-Yau spaces. There's so many different spaces that string theory can live on, that and the basic size of the string is likely to be so small. We're not hoping to see them directly. I don't think that there's much. I don't think it's a one has to gamble and in your scientific pursuits, it's not a logical impossibility that somebody will find just the right solution of string theory that matches exactly with everything we observe in nature. But it's
Fair enough, but okay, so you're talking about
so a lot of that happened, but then there was also a lot of structural work on just understanding the guts of how string theory puts together quantum mechanics and general relativity. And to do that, you need to go beyond perturbation theory. And that is just scattering of weakly coupled particles. You needed to be able to talk about, black holes and other kinds of things. So a number of people, myself included, started thinking about that kind of problem. And indeed, I had other, I've been thinking about black holes also since like my thesis, and trying to understand various things about them, and had various enterprises which involving black holes, which had nothing to do with string theory at all. And then there's this thing about Hawking's puzzle about the entropy of a black hole. So there are really two parts of Hawking's puzzle. One is he had this formula whose derivative is on his headstone now. The Hawking temperature, the number of a formula for the number of gigabytes that you can store in a black hole.
Oh, so him and Boltzmann. So he and Boltzmann have a similar.
Hawking has the derivative on his.
Okay.
He's got the Hawking temperature.
Okay.
But anyway, the Bekenstein-Hawking entropy formula tells you how many gigabytes there are in a black hole. And so there's two puzzles that's raised. Where are these gigabytes? Black hole's a hole in space. How do we understand that? And the other is, how does the information stored by the gigabytes go in and out as you make a black hole?
Right.
And then let it evaporate. Okay, so now, other kinds of theories, you can't add anything to string theory without spoiling its consistency. You can't add more parts. It's not like quantum field theory where you can always add in another particle if there's something that doesn't match up. Our standard model, dark matter isn't working, so people just add another field in. You can't do that in string theory. You have to take what's given to you. And so string theory, if it were, string theory solved on paper the mathematical problem of reconciling quantum mechanics and general relativity. But there's another big problem, which is Hawking's problem. How do you account for the entropy of a black hole? And so this was kind of when we first started, when a lot of people started working on string theory in the 80s, we didn't have the technology, the computational ability, the analytic techniques to address this problem. But over a 10-year period, we amassed it. And we learned really a lot of things about how you do calculations. And it was sort of a moment of truth for string theory, because at one point I realized that we were rapidly heading to the point where we were going to actually be able to do this calculation. And it had better get the right answer. If it gave the wrong answer, string theory would be dead. And we had this sort of growing toolkits of analytic methods. And so once I realized that we were going to be able to do this, I was working on nothing else. And it took me some number of years, but finally I got a formula and it matched perfectly. So, that was, I think, a victory for, it was a good a good a signpost that we were on the right direction. Because,
so just to understand that, how do you set up a black hole in string theory? I mean, so you're interested in the number of microstates of the black hole consistent with its macroscopic structure, and the number of microstates as measured by, string degrees of freedom or something. How do you define a black hole in string theory?
Okay, so one of the really important things here is this idea that we had been starting to understand within a lot of, analytic detail, is that things can have two completely equivalent descriptions. And as you go from, if we, a simple example, if you have the function 1 over 1 minus x, you can expand it in x near x equals 0. But, if you're at x greater than 1, you want to expand it in 1 minus x. Okay, so different functions can have different, in mathematics, they can have different expansions, different radii of convergences. And as you dial some parameter like x, depending on where you are, one expansion might be better than the other.
That's back to your Reggie theory thing. It's back to the T channel and S channel exchanges being equivalent.
Right. And depending on what scattering process you're considering, you might be better off summing over T channel poles. You have to do a lot of work. If you're in the wrong kinematic regime, you'd have to do a lot of work to sum over S channel poles, but T channel poles, you could get a good approximation with a couple terms, some other regime. Okay. Now, we showed that for some kinds of black holes, the number that there's what's called a topological index, that the number of microstates, sort of weighted number of microstates, could not change as you change this parameter. So it's a topological invariant.
So which parameter now?
Well, okay, so there's a parameter which takes there's one object that you can, so the parameter would be the coupling constant of string theory. There's a coupling constant, the string coupling.
Which is the string tension, basically.
No, the string tension is dimensionful.
Okay.
It's the strength with which it tells you the likelihood for one string to split into two.
Okay.
Okay. So you can dial that parameter.
Mm-hmm.
And so you have an object which we found an object which has the property that for one value of the parameter, the best description of it is as a black hole, is to use the Einstein equations and describe it as a black hole with an event horizon and an entropy that can be computed using the Bekenstein-Hawking formula.
But so I don't understand. As you've described it, you've got these strings and they're propagating in some background space-time. Is that the right picture, or should I not think about it that way? I mean, in your Calabi-Yau setup, as I was understanding it, you've got these string objects and they exist, you look at the strings, living in this background space-time. How does the black hole, is it a string living in a background black hole space-time, or how does the black hole enter the whole picture of the strings?
Okay, so okay, so there's a parameter. Let's see. Okay, I'm gonna oversimplify it a little bit, and if you catch me, which you probably will, you'll force me to give a more detailed explanation. But there's a parameter which is the string coupling, which when it's large, there's a solution of string theory which we can describe for any value of this parameter. But at one value, when the string coupling is large, this solution, this object, looks like a charged black hole described as a solution of the Einstein equations. That is the best description of the object, and strings propagate around on this background. But it's a fixed solution.
But so when you're talking about that, I mean, from your description of large coupling constant means strings. I mean, if we think about the graph of sort of interactions of strings interacting and so on, we presumably can look at the kind of the skeleton of that as a graph. And so this is then a graph that has a larger number of nodes in it. And you're saying there exists some graph that is some special graph that has some rate of generating new nodes and so on. Is that a reasonable way to think about it? What's the characterization of this object that is the large coupling limit of string theory?
Let me say another part. There's a second description of the same object.
Okay.
I'm being a little, let me be a little bit more imprecise about what the parameter is. So there's a parameter that is a constant in the theory. You can tune it. You can find this solution of the theory for any value of the parameter. For one value of the parameter, it looks like a black hole. For another value of the parameter, it looks like a bound state consisting not just of strings, but of these other objects called D-branes that we discovered in the mid-90s. They're kind of higher dimensional extended objects, some very complicated bound state of all those objects that you can describe. It's an ordinary quantum system. You can describe it and you can compute exactly how many microstates it has. Then you can show that as you vary this parameter, that number of microstates is in kind of topological invariant and can't change. And when you vary it back to the regime in which it looks like a black hole, you find that it matches the Bekenstein-Hawking entropy.
So the thing I've still not understood is how do you make any correspondence between this string theory and black holes? Why is there any, I mean, you know, they seem like, other than the background space-time in which the string lives, where do you get something that looks like a black hole in the theory of strings?
Well, so we can think of string theory, so different ways of finding solutions of string theory. So the oldest one would be this. You could think of string theory as a theory which has some light degrees of freedom, like the graviton, the electromagnetic field, and then a bunch of massive stuff, massive string modes. And we can use an effective field theory in which we ignore all the massive stuff. And we know exactly what that effective field theory is. We know exactly what that effective field theory is. A lot of it is determined just by symmetries, and we have other ways of determining the rest of it. And then we can take that effective field theory and find solutions of it. And as long as those solutions, you know, are any parameter of the solution is large compared to the size of a massive string, it should be a good solution. So we take this effective field theory and we solve it, and we find that there are black hole solutions. And in fact, in this instance, we're interested in black holes that carry charges, electromagnetic charges of various kinds. And we need the charges in order to make the topological invariance argument, actually.
But so, for example, the event horizon of the black hole, what is its interpretation at the level of looking at kind of the dynamics of strings?
At this level, we are treating strings as, you know, you have some solution which is given by effective field theory, and you're just describing it in the usual language. String theory reduces to general relativity in this limit. So it's just the standard general relativity description.
But so, okay, so then the effective field theory is only looking at these excitations on the strings. It's not sort of telling you, it's not telling you, I mean, if one was to look at, I'm just trying to get some sort of intuitive picture of what does a black hole made from strings. So what you're saying is it's not really a black hole.
In this picture of the object, we're using the effective field theory that string theory reduces to, which is Einstein-Maxwell gravity. And then we're just describing it as people would have described it in Einstein-Maxwell gravity 50, 100 years ago. So we're just, yeah. So there's nothing very stringy about this solution.
Okay. So all the other features of general relativity would also occur. I mean, any other, is there a big bang, for example? Could you have a big bang-like thing? Can you have energy momentum? Or is it vacuum Einstein equations?
You can have energy momentum. There's a Maxwell field, among many other things.
Okay, so you should be able to have things like big bangs and so on.
Well,
as well as black holes. You
have to be careful, because at the Big Bang, the curvature gets very large. And so the effective field theory description, the ignoring of the massive stuff, would not be valid.
What about at the center of a black hole?
Also at the center of the black hole.
But that doesn't matter for your purposes. It doesn't matter. There's kind of and maybe a Reisenau-Nordstrom black hole has a more complicated singularity structure anyway.
Right.
Okay.
There are actually some objects sitting there. Yeah. Yeah. So then that's one description, but now we have another description of the same object. And right, so that now we have another description of the same object that we get by dialing this parameter. And in this other limit, it looks like a very different kind of object. The horizon sort of melts away, and you see a bunch of a big cluster of D-branes and strings, and that has a bunch of modes of it, and the modes of those you can count, and their entropy numerically matched what you got from the Bekenstein-Hawking entropy formula. And if this hadn't worked, everything would have been inconsistent.
But so what's your intuition about what's going on here? I mean, so in other words, you have, like for example, in our models nowadays, we have a pretty clear idea of how, what the event horizon, what this entanglement horizon that we figured out looks like for a black hole. And we can give a sort of a more or less intuitive description of what, the structure of space-time and quantum mechanics looks like around a black hole. And I'm just sort of curious, in this kind of string picture, is there kind of a
it would be great. It would be great if you could count and reproduce the Bekenstein-Hawking formula.
All right, so Jonathan, is Jonathan here? What does Jonathan have to say about success or not in doing that? I think that's a current project.
Yeah.
Yeah, it is, but it requires at least defining a non-interacting QFT, which we're working on, but we don't yet have a complete formulation of.
Yeah, because I mean right. So okay, so hopefully we will be able to. I mean, I'll be surprised if it doesn't work, because enough stuff fits together with this that it should work. But okay, so anyway, so I haven't.
So this was the beginning. Then there was a lot more that happened, which is when you looked at this thing, the other description, the sort of dual description of the black hole, it turned out that this thing that I wasn't very explicit of, it was actually itself weirdly could be described as a little loop, not of string, but of something else with many degrees of freedom on it. And it was a described by conformal field theory in 1+1 dimensions. And so we turned a black hole into another mathematical object, a conformal field theory, and showed that there was an equivalence. At that time, we only knew that there was equivalence in the number of microstates, but now we know that there's actually a complete equivalence, all the quasi-normal modes, all the, everything you want to say about a black hole, it's a complete sort of dual description. And this is now known as holography, that black holes have this alternate description in terms of a field theory in a lower dimension.
Right. But so okay, so that's been a big theme for the last 15, 20 years or something.
Yeah.
And so, at this point, okay, in our models, there's a pretty clear path for understanding how that works. And it has to do with this branchial space versus physical space and so on. And I'm curious what the current kind of, and I suspect that there has to be a pretty close correspondence between what has happened in holography and the kinds of things that seem to work in our models. But I'm curious what what's the intuition now about why holography works? I think we have a version of that intuition based on the assumption that what we're doing works the same way as holography. But I'm curious what another kind of point of view about why it works is.
Well, why it works. I think it looks incredibly, at first sight, it looks incredibly far-fetched, and that you could have examples. Now, of course, we're always talking, I'm spending a lot of time trying to understand the real world. We haven't really talked about that. We've mostly talked about string theory, but but the fact that you could have this structure seems very surprising. And it enables you to, get out of what seems like, inescapable traps of how you can consistently, have a black hole be a hole in space, yet have all these degrees of freedom and various puzzles in quantum gravity. So, I think it works in string theory because, my guess is that it's a real structure that exists in the world, not string theory itself necessarily, but the holography, which is sort of a meta phenomena within string theory. It could exist in the real world. It could exist in bronchial space. It could be.
See, I think, in our kind of setup, there's this kind of way in which space-time is built, and there's a way in which the kind of paths of quantum history are built, and they are very structurally similar, and that leads us to have essentially physical space and space-like separations, and also branch-like separations. And those two, there's sort of a close correspondence between those things. They're structurally basically the same kind of thing. So in other words, what happens is that, as the Einstein equations operate in physical space, so the path integral operates in this branchial space. And that's, it will be very nice. And we've talked about only rather general and historical things here, but the thing that we'd love to understand is, I suspect that there is a really pretty close correspondence between the kinds of things that we've set up and the kinds of things that probably already know in string theory, or in whatever you call it, in holography, whatever
Yeah.
you call it.
I mean, no, I agree with that. And one of the things that looks familiar is like, we used to think, or I used to think that, the way to think about quantum mechanics was you have a classical system and then you quantize it. And, there's a parameter, the Planck's constant and some limit, and that's certainly how it works in QED and the standard model. But here we've run into much more complicated things where when you have these different descriptions, what's classical from one point of view is quantum from another point of view, and vice versa. So there is no sharp distinction between classical and quantum, and that's sounding like your, quantum mechanics and general relativity getting exchanged when you.
Yeah, right. Well, I mean, for us, the story of quantum mechanics is really the following thing. You have these rules, for example, and you might think you just apply a rule, you apply it again, you apply it again, you get a single sort of thread of time. A key picture here is these multi-way systems where you end up getting these many threads of history that branch and merge and so on. And when you look at this whole graph of branching and merging things, and you take a slice of that at a particular time, that's our branchial space thing, which is kind of a map of quantum states. And there's a long story here, but this is, the thing that I'm sort of trying to understand. So I mean, given the, what you're saying is, at this point in the string theory world, there isn't a particularly clear, it's obvious this has to work type of story yet. I mean, to us, it seems like it's sort of obvious it has to work. And I'm guessing, that's what I'm curious about.
I would say certainly in the string theory world, it wasn't obvious in the 70s, early 70s, that it had to work. But now people are wondering about many things, but they're not really wondering about whether it does work.
No, I mean the holography principle. The
holography principle. Yeah,
right.
It we know that it does work in some special contexts,
yeah,
anti-de Sitter space, but whether it is a general principle that you can think about in any space-time, it seems like it should be, but we don't.
Well, I think for us, so here's what we would guess, right? So for us, holography would be the fact that this multi-way causal graph that we build from a mixture of space-time and quantum mechanics, the fact that projecting that in sort of two orthogonal directions in some sense is that it's equivalent when you project it in those two orthogonal directions. That will be an example of sort of perfect holography-like behavior. And so it wouldn't be surprising if that was only strictly true for certain particular multi-way causal graphs, but that there was still a sort of conceptual.
Is that holography or duality? So there's some dualities are not holographic, right? They relate one quantum field theory to another one.
No, I don't mean those kinds of things. I don't mean, whatever, sine Gordon and massive Turing model. I don't mean those kinds of things. No, we're talking about ADS CFT, like holography, duality, whatever you call that.
Yeah.
Right? We're talking about the correspondence between a structure in space-time and a structure in essentially quantum space. Right? That's what
I see.
For us, what's going on is that there is a structure that gets laid out in space-time. There's a structure that gets laid out in this thing we call branchial space, which is essentially a space of quantum states. And the thing that I'm describing is there is this structure that knits those two structures together. Those two structures are inevitably just different slicings of this multi-way causal graph. And so, but there's a single object that encompasses both of those things, and different projections of it represent what's happening in space-time versus what's happening in essentially quantum mechanics. And so,
Stephen, I have to go in like 10 minutes, and I'm just noticing there's all these comments on the chat. I'm just wondering if like anybody has a
Please,
question?
yes, we should do that. Let's see. Raphael is asking about quantum field theory and string theory work to X decimal places. That's a complicated story. Let's see.
I guess so, just looking for the minimal example of to get your hands dirty. So when we say like, hey, quantum field theory, it can predict this particle's property. Is there like a, I don't know, like a simple or some sort of open source data set where they sort of take the measurements from the collider, they have it there, and there's like
no,
a
you do
program.
a lot of Feynman
Okay.
diagram computations, and they take years of computer time these days. And you know, the end result is
Whole careers have been started trying been started out trying to solve this problem.
Yeah, Andy is mentioning is describing my I mean, I started out trying to do those kinds of things. Yes. It's so let's see, were there other things here that I think
maybe somebody has a question.
Jonathan.
I have a historical question.
Yeah.
So this is a question for both Dr. Andrew and Stephen. So, okay. So in technology, sometimes happens like in blockchain technology, the technology behind the cryptocurrency, that people say, oh, this technology is not producing any real applications and it will die soon. So can you relate that to the history of string theory and the community around?
Well, I think that it has. I like to see the person who's talking. I can't find you here. Okay.
Oh, sorry. Let me turn on my video.
Actually, we should. I want to make sure that Jonathan gets his opportunity to ask something that I suspect is more technical here.
Okay. No, but string theory has produced it has produced a lot of new results, new directions to go in, new connections with other fields, and so that's what's kept it, that's what's kept it alive. But I'm sadly afraid that it might not be true in science, in academic science, that fields can stay alive for a very, very, very long time.
Well, I mean, the question
without any new. It's an unfortunate feature of
Well, I think one way to state this question, which I think is perhaps an interesting version, is: are there fields which develop significant technical depth and just turn out to be forever irrelevant? That is, string theory developed significant technical depth in the 60s and 70s and so on. And, just like transfinite numbers developed significant technical depth by the beginning of the 1900s. Yeah. And the question is it the case that any field that develops significant technical depth will eventually find a home somewhere? And the answer to that is actually fairly positive so far, that most things that have developed significant technical depth, while their original application might have been just off base, the technical, by the time there is a formal system that is capable of supporting significant technical depth, it usually eventually has a home, even if it wasn't the original home that was intended. I mean, that would be my sort of analysis of the string theory story.
I would totally agree with that. Yeah.
Let's see, Jonathan, you said you wanted to ask something about holography.
Yeah, so I wanted to get Andy's perspective on just how general the concept of holography, how general you think the concept of holography is, and how specifically related to the formalism of string theory it is. So specifically, I wanted to ask, okay, as you undoubtedly know, and as you kind of alluded to, there are these various generalizations of the ADS-CFT correspondence to cases where there isn't an obvious like string theory parent to the duality, right? So in cases like Kerr-CFT correspondence or the hydrodynamic generalizations and things, Now, okay, in some of those generalizations, like when you relate a gauge theory to a supergravity, or quantum supergravity, or a classical supergravity, or just classical gravity, you can sort of say, okay, that's some kind of limit of the string theory. So ultimately, string theory is still lurking behind there somewhere. But with something like the Kerr-CFT correspondence, it's quite unclear, like what the string theory sort of, as I say, the string theory parent, or the string theory predecessor to that duality is. So the question I'm asking is, do you think holography is something that will ultimately turn out to be intricately bound up with the formalism of string theory, or do you think it's just a much more general consistency condition for theories of quantum gravity that actually will end up applying and appearing in many different formalisms, many of which will be incompatible with sort of string theoretic foundations?
Well, I think it's that's a great question, Jonathan. And I think it is much more general than string theory and ADS-CFT, but I can't prove that statement. It just would strike me as weird that, I mean, I'm a believer that the real world is a more mathematically richer and interesting place than anything we construct on paper. And this is a really cool thing, this holographic relationship. And so it just I think it's true, but anybody who tells you they can prove it is
we'll see if
wrong.
Jonathan can, in another few months, we'll see if Jonathan can make that statement. But so I'm curious, are there near misses of holography? Are there things where it almost works, but it doesn't quite?
I don't think so. And also, we have to distinguish, it's important there's a sort of top-down holography and a bottom-up holography. So the things you associated with string theory are top-down holographies, that you started with a theory which was completely well-defined mathematically, namely string theory, and you really showed it was really shown, and it's as rigorous as we get in theoretical physics that this holographic principal relationship exists in certain situations. But before the sort of stringy version of ADS-CFT, there was work by these guys, Brown and Hanot, who were studying anti-de Sitter space in 3 dimensions, but not in string theory, anti-de Sitter space with anything. And they did an analysis using just symmetries of general relativity and careful asymptotic analysis of the symmetries. And they found some conclusions that were very, just using low energy analysis, they found some, basically came very close to showing that ADS3 was dual to a 2-dimensional conformal field theory. They showed that there was the action of a conformal group. They computed the central charge, all of this without knowing any microphysics. And so I think in the real world, I don't think in the real world we can hope for a sort of top-down holography, because top-down holography requires understanding in perfect detail all the laws of physics, and I don't think we're going to get that. I don't think you guys are going to get it either. I don't think you're going to get the full spectrum of particles I assume that you're doing some kind of bottom-up. I mean, maybe I'm wrong, but getting the full spectrum of particles, predicting anything that will ever be seen at any accelerator, that doesn't seem like an enterprise that I would. It just doesn't seem likely to succeed. Okay, but now bottom up.
Why do you think that? I mean, do you think that there isn't a fundamental theory of physics?
I think that I don't think we're anywhere near. First of all, it might be okay. I don't like the landscape, but there might be many consistent universes, and we happen to live in one of them. And
I think a more likely possibility is that the way in which we observe the universe defines what we see in the universe. And that the fact that particles, that the electron-muon mass ratio is the way it is a feature of our particular sampling of the universe, of effectively what can happen in the universe. I mean, that's my guess about how it works.
okay, but all right, I'm interested in what I can do next. So, and
I think you're far away from that point.
I think we're far away from that. People, string theorists talk about it a lot. I don't think we're close to it. But I do think that there's a lot that we don't understand about the consistency of low energy physics and so on, and that a bottom-up approach to holography, understanding why it has to be true.
I really think, I mean, I have to say, from what I can see, the formalism that we have, which you can think about in terms of fancy higher category theory, and you can think about it in a bunch of different ways. I think, from the things I've seen, it has the best chance to actually be an explanatory, a sort of easy explanation of why such correspondences exist. And, it will be really worthwhile to actually figure that out in more detail, but it seems like it has all the right elements, and it seems like it has the right sort of flavor of of how things seem to fit together. But it's interesting to hear and the guess would be that there's a very broad class of things that show roughly holographic-like correspondences, but that it only in particular examples will it be a precise, you can just make this, this parameter maps to that parameter type story. In other cases, it'll be more approximate or more, more just in a class of things, there will be ones that correspond this to that. But it's some, and I think yes, the mission of, explain the electron-muon mass ratio is also not something that I expect to happen quickly. And I suspect that the end result of that will be, as I say, that it is a story of understanding observers better than we do right now to know why it works that way for us. And I don't think it has to work that way for us. I don't think it's the case that there are, you can just sort of throw a dart, pick a universe. I don't think that's the way it works. I think that it depends on certain features of us as observers of the universe that cause us to perceive the universe that we perceive, which is a slightly different thing than saying it is, that it's sort of an arbitrary thing where we're not.
It's not slightly different. It's radically different, right? All the I think it's logical. I'm not saying radically different in a bad way, but that is in a way, the most different thing about your approach, right? So the laws of physics as we usually discuss them, you could have a physical universe with no observers in it, right? We assume that there's a reality to the initial, and it's a pretty weird assumption. It's a pretty unphysical and weird assumption. And it's interesting that it seems to be work so far and consistent with.
What seems to work?
That we have laws of physics in which the observer doesn't play an essential role.
But it does. That's the point. If you imagine, if you were very different than you are, if you were, the fact that you perceive, for example, space to be something where you can say at some moment in time, space just exists. That's a feature of the way that you observe space. In other words, if you were, for example, we
Stephen, I'm thinking you're saying it should, not that it does. I'm just saying that in the textbooks, the
textbooks. But one example of textbooks that don't work that way is statistical mechanics textbooks. Your statement, a statement like entropy increases, right? That statement depends on coarse graining. That statement depends, without coarse graining,
that is true.
There is no entropy increase. And coarse graining is a story of observers, basically. And always, and by the way,
but in the prevalent reductionist view of physics, that's epiphenomenal, right? That
yes, perhaps, but I mean, in general relativity,
which I think could well be wrong.
Right. Well, relativity also depends on the observer. I mean, relativity is a story of sort of being realistic about the observer, as quantum mechanics is to some extent. But the sense in which those theories depend on features of the observer hasn't been quite as clear. I mean, and even in statistical mechanics, it's a mess. What is a valid coarse graining? What is not? I think we know how that works now. It's a, you know, computationally bounded observers are what correspond to valid coarse grainings. Anyway, there are lots of interesting things. It would be nice, perhaps. I mean, we're hoping at some point a much more technical deep dive into the correspondence between. I mean, and I don't know. I'm curious. In your stuff, do the category theory people, do they enter your world, or is that still a separate world? The higher category theory.
The category. I mean, you hear the words category theory.
Okay, but that's about it.
No. Some people say it often. I haven't. I think category theory has to be used for a precise description of D-branes. I don't know.
Doesn't surprise me.
Yeah.
But I'm curious, maybe Jonathan or Xerxes or somebody can say, I mean, if we were going to look for sort of formal correspondences between the kinds of things that Andy is doing and the kinds of things that we do, I mean, we've now made good correspondence with higher category theory, we've made good correspondence with causal set theory. Maybe we've made decent correspondence, we'll understand it probably better in a few weeks, hopefully, with causal dynamical triangulations and things. There are these various different kinds of theories with which we think we understand the correspondence. We don't think we understand the correspondence with string theory. We think we qualitatively understand the sort of holography story, but not in more detail. So I'm just sort of curious, Jonathan, for example, do you have what will be your approach to making a more formal correspondence between these things?
Well, in a sense, one of these approaches is something that we actually have a summer school project on this year, which is so asymptotic safety in things like string theory. One way that you can get sort of regularization of the gravity path integral is you just impose effectively, you introduce a sort of lattice regularization, right? You say I'm going to impose some energy cutoff which regularizes my path integral, and it's known that in, say, the 1+1 dimensional case, the path integrals you evaluate using that kind of regularized lattice gravity, they give you exactly the same scattering amplitudes and things as you would get from bosonic string theory, from 1+1 dimensional bosonic string theory. And there are already a bunch of sort of pre-existing connections that are known between things like regularized lattice gravity and, particularly bosonic string theory, the scattering amplitudes computed there. So we think that we have a fairly well-defined program for essentially redoing those lattice gravity calculations in the context of multi-way causal graphs, where effectively you're generating a multi-way causal graph as as some initially like a Euclidean triangulation or something, of some known manifold. And so there should be a direct way of seeing whether the scattering amplitudes you compute in that framework, accord with the scattering amplitudes you computed using, say, world sheet diagrams in bosonic string theory. And that would, at least that would be, I think, a nice initial consistency check that the formalisms are actually compatible. There's obviously more stuff to do beyond that, but I think in the short term, that's something I suspect we can potentially achieve, within the next couple of months.
Guys, I just realized I'm in a little trouble here.
Yeah, you're beyond the allocated time.
I really got to go. So great.
We appreciate
great fun. Great fun.
Yeah, right. Thanks a lot.
Okay,
Thanks.
bye.
Thanks.
Bye.
Okay, bye-bye.